check and make sure that that is in fact the case. Sorry for being a little bit late today. OPS is being more like slow BS. That's an echo that you definitely heard. Okay, I got that fixed. I was working on a paper and I looked at the clock and I was like, it is very close to 4 o'clock. I better go set up my system. So I'm a little bit late today, but hopefully worth the wait. Today, we're going to be doing some deep learning. I'm excited, I guess. I don't know. Yes, I am excited. I also had too many donuts today for National Donut Day, and I am very full of donuts, and I really want a nap. So this is going to be naptastic. Oh, and let me really quickly tweet that this is happening so that people know about it. Okay, so today, as I think I mentioned, we're going to be doing deep learning. And specifically, I'm interested in predicting emoji. So given a string, I want to be able to predict what emoji is going to occur in that string. And I think a sort of a smaller search space, I'm going to start with strings of emoji and figuring out what emoji would possibly complete this string. I'm just going to real quick. Excuse me, tweet that this is happening. Oh, so full of donuts. I'm so full of regret. They were so good. Okay. And I'm, instead of writing things from scratch, because I am a big proponent of never writing anything from scratch unless you absolutely have to, I am going to be starting with Dan's kernel. And this is a really nice introduction, because it has, you know, all the stuff, but also because it shows us how to use GPUs and kernels. And I believe that the GPU part is further down. Beep, boop, boop, beep. Because I think there's a bit where you have to say, you have to enable it. Not this one, not this one. So you have to turn it on, and we'll go over how to do that. I was going to spend more time going over this in more detail for myself before I got started, but then again I got sidetracked. Okay, so let's go through Dan's kernel first, and then start doing ours. So he's using, I'm sure, convolutional neural networks here. And for sequence predictions, we're probably going to want to use LSTMs, or long short-term memory. Yeah, 2D convolutions. So a lot of this sort of like model specification, we're going to have to completely redo, because these would not make sense for text data. Although there are some people who have been using convolutional neural networks for sequence data. I remain unconvinced, but we'll see. It's an empirical field. Lima Sigor asks, this live will be available to watch later. Yes, all of these will be on the YouTube of Kaggle, which is typing, which is kaggle.com, all spelled out as a single word instead of just Kaggle, because that's somebody else that isn't us. Yeah, so let's start by going through from top to bottom and then figuring out what we'll need to change for text, and then actually going through and changing the things. So this is going to take, I think the thing that's probably going to take the longest is our data preparation. And then the model specification, I think, is also going to take quite a while. Not because it's super hard. Lima says, I'm trying to watch, but it's always loading. That's unfortunate. I'm sorry to hear that. Hopefully it just stops that and then you can actually watch it. Oh, okay. So I think that the data preparation and processing is going to take us a long time. I think the model specification will also take a fair amount because I'm going to be doing a fair amount of guess and testing. And even with a GPU, that's going to take a minute to try different things and figure out a model architecture that works well for what we're doing. And then, I mean, writing of this code will not take long. It is the fitting and then comparing our various fitted models to each other that's going to take a little bit. All right, so let's get started forking this notebook and then going through and running Dan's code and then modifying it. Okay, so the first thing we're going to want to do is, I don't care about that, make sure that we have our GPU turned on. So this is going to be under settings. And if we scroll down, we see that our GPU is enabled. So we're all good to go because we forked a notebook where the GPU was enabled. And this is a NVIDIA Tesla K80, and we have 6 hours of runtime. Yes, it is available. It's fairly new. And depending on load, there may or may not be a queue. But yes, we do have GPU support. So we should be all set up here. And I'm just actually going to get rid of this whole block. Sorry, Dan. It was very helpful, but I don't need it right now. So the data we're using for this sample is these photos of hands that we can't see previews of them, but believe me that they are photos of hands making various American Sign Language? Yeah, American Sign Language hand shapes. I ask if it's American Sign Language because many of the African sign languages have the same hand shapes because they were developed by missionaries. Yes. And in fact, it is the same GPU available on both Colab. Lima Segura says there's GPU support on Google Colaboratory as well, which is true, and they are the same GPUs. So just at the moment. I mean, who knows where things will go. Okay, so these are hand shapes. And this is sort of like a slightly more interesting version of MNIST, which is identifying the numbers, handwritten numbers from their sort of little pixel pictures. All right, so we're importing a bunch of stuff. We're using Keras, which is a high-level library for specifying what your model will look like, so you don't have to do a lot of stuff. When we use this, we're probably going to be importing LSTM instead of convolutional two-dimensional neural networks. Sequential we'll probably want. We're probably not going to want this image data generator for text data. We're setting the seed for reproducibility. This is a very good best practice. We're doing it twice. So maybe this is for the data preparation and this is for TensorFlow, and they're looking at different seeds. And then we're just going to look at some of our raw data. So this will import a bunch of stuff, and then it will show us what some of our data looks like. So here we see some examples of a hand making the hand shape for the letter A. And now we're going to see some for the hand shape of the letter B. And as you can see, the lighting is different, and in this case, it's mostly the lighting, but here it's in different parts of the frame, and the angle's a little bit different. It does look like the same person's hand, which might be potentially a limiting factor if we wanted to use this. And I just want to take this point to say, we are not building a sign language recognizer. That's absolutely not what's happening here. Sign languages are very complex. You can't look at just the hands. You have to consider the body, the facial expression. You have to consider, places in space and reference back to the same place in space. So this is in no way a sign language recognizer. It is as to recognizing a full sign language as being able to recognize the MNIST digits is to being able to do calculus. There's a world of difference. Sign language was one of my research interests in grad school, so I have strong feelings here. All right. what are we doing here? So here we're saying that we want a 64 pixel by 64 pixel little square. And then we're going to create a 3-dimensional tensor where the first dimension is red, the second dimension is green, the third dimension is blue. We have 29 classes for the 29 letters. The 29 letters. Let me just look at the data real quick. Are there 29 letters? So, there's 27 letters, right? Am I making that up? There's not 29 letters. Y'all, I feel real dumb right now. How many letters are there? There we go. 3 classes are for space, delete, and nothing. Ooh, okay. I thought there were 29 letters, but it's late enough on a Friday that, you know what? Maybe I'm just wrong about things. Not that I can't be wrong about things not late on a Friday. Space, delete, and nothing. What? Those aren't things that people sign when they're finger spelling. It's a little bit weird. Okay. That tells us why there's 29 classes, which was surprising to me. Let's scroll back down to where we were. Batch size and val_frac. Oh, how much of our data we're going to put in the validation split. So we are training on 90% and validating on 10% of our data. And then the batch size is just the batch size. And so we're going to augment the data. Sample-wise center. Image data generator. I'm not super familiar with this function. I don't think it's going to be relevant to us with text data, but I'm interested to learn more. All right, tell me more. Keras documentation. I don't know. Something about this this particular web design gives me like a visceral reaction whenever I see it. Generates batches of tensor image data with real-time data augmentation. The data will be looped over in batches. Okay. Computes the internal data stats related to data-dependent transformations based on an array of sample data. Sample data. So is this like flipping and twisting and distorting the various images? I don't work that much with image data, so a lot of this is like, that sounds reasonable to me. The script for more details. Batch size. Directory iterator. All right. Points outside the boundary of the input, nearest, reflect, warp. Default is nearest. Points outside the boundaries of the input are filled according to the given mode. All right. Not entirely sure what we're so I know what we're doing. We're taking our images that we already have and we are creating additional images from them to train, to feed to our model to train it. I'm not entirely sure what we're doing to the images. It seems like we might be height, shift, range. It seems like we might be changing the edges to be the same as the outer pixels? Maybe? Shrug. Okay, let's run this. It's probably going to take a minute. So with text data to do augmentation, you'd probably do, it's rotating images. Haha, thank you, Sri. With text data to augment data, usually you have like a sliding window. So like you're looking at like the first 5 letters, and then you're looking at So you're looking at letters 1 through 5, and then you're looking at letters 2 through 6, and you're looking at letters 3 through 7, and then you're looking at letters 4 through 8, and so on and so on. So you have sort of like a little sliding window, and that's how you augment data with text, generally, if you're going to do it. But like I said, I've spent less time using image data sets. All right, and now we're describing the size and the shape of our model. So the input layers should be the same size as our input data so that it knows what to map to what. And so because we had 64 by 64 was our pixels, was our target size for images, that's what we're going to start out with. And then you can see the input shape is the shape of the same size as the data that we're inputting. And then we have a second layer that's basically the same, except there's a difference in strides. It will prevent from overfitting. Yes. Data augmentation will prevent from overfitting. I think strides is how many pixels you move over with convolutional neural nets. Let's look this up too. Actually, I just went an image. Yeah, so that's how many pixels it bloops over, I believe. And so a stride of 1 is moving over 1 pixel, and then a stride of 2 is moving over 2 pixels. So we have 2 layers, and then we do dropout, so we sort of kick out the nodes that aren't doing much. And then we have a larger layer, and then we do a smaller stride, and another layer with a larger stride, and then we kick out the nodes that aren't doing much, and then we have an even larger layer with a stride of 1 and a stride of 2, and then we flatten everything down, and then we kick out the useless things again, and then we create a dense layer where every node is connected to every other node, and then finally we take that layer and we get our output out of it, right? So it is this layer that is taking, you know, all of this information and giving us our label, which is why the activation is different. It's taking sort of the most likely label, and all of these are using rectified linear units, which are sort of look like this, which is an activation function. Because you know how in like with nerves, they're either on or they're off, and they sort of sit there off, waiting for the signal, waiting for the signal, waiting for the signal, and then they get enough of whatever it is built up, and it goes bloop, and it turns on. And that's sort of like a linear function, and in deep learning, we tend not to use like the actual functions that I want an image. There we go. We tend not to use the actual functions that an actual brain would use. We use a function that's always goes to 0 if you're below 0. So it can sort of, the downside of that is it can end up killing nodes in your network. You can have nodes that are never activated. But since we're using dropout and we're kicking out the useless nodes, that's not a huge problem for us here. Generally in text processing, I tend to see rectified, not really, what is it? The one that's it's got like a little bit of a drop off, so it doesn't go straight to 0. And I'm blanking on the name of those. Oh my God. Leaky. I tend to see people use leaky ReLUs more often than just plain ReLUs. But I think that's just a difference between text processing and image processing. All right. Actually, I could have been training my model the entire time I've just been sitting here talking. So I'm just going to start fitting this, and we can keep going through this because this will take a minute. So once you have in Keras, there's sort of like a very high level thing. So this is where you describe the shape of your model. And when you are presenting your work, this is what would determine what those little like diagrams that people show you would look like. Oh, my desk is very squeaky. And then once you've specified what your model is going to look like and your data sort of goes through it, so from 1 to 2 to 3 to 4 and all the way down, hence sequential This is a type of model within the Keras models that we're building. We have to compile, so we specify what we want our optimizer to be, so how we choose to, specifically how we move towards a more optimum output given our input and our feedback on whether we were right or not, and then how we're looking at loss. And you can play with these. There's a lot of different options for them. And then also what metrics you're going to record. So here Dan's just recording accuracy. I tend to like having more metrics because I'm that kind of nerd. And then you train the darn thing. So sort of the general idea of training is that you basically start randomly and you push all your data through, and then you get to the end through this network. I'm using my hands a lot and y'all aren't seeing it. And then you get to the end and then you find out whether or not your label was right, and it's probably wrong the first, couple hundred or 1,000 times. And then you get feedback the direction that you were wrong, and it propagates back through the network. And then you try again with the next image and you make a guess and you find out whether you were wrong or not, and then you go back through the network and back and forth and back and forth and back and forth and back and forth. And then of course, every so often we're just gonna kick out the nodes that don't have utility to us. Yeah, and that's just gonna take it a while. Although this is pretty fast. So we have 5 epochs that we're doing, and it's gonna take us about another 1.5-ish, and you can see that the loss is going down and the accuracy is going up. And I believe in the final model that, sorry, I'm a little bit loud, I didn't realize that. In the final model that Dan shared, the final accuracy was around 80%, which on a 29 class problem is pretty good. I would be happy with that. So the main things we're gonna have to do to turn this into a text model is first we can just get rid of all of this. We don't care about any of this image stuff. So we don't need to import the image data generator. We can just kick that out. And we don't need to do this type of augmentation, but probably we're going to want to do some sort of data augmentation using that sort of like sliding window I was talking about. The structure of our net is going to have to be very different, and the model fitting will pretty much be the same. Ooh, is she stuck? What's going on? GPU's on. Oh, we're going into epoch 2. So we're about 1/5 done. All right, so I think what we should do now, while we're waiting for this to train, is go ahead and figure out what data we're going to use for our problem. So I mentioned that I'm thinking about starting with just a string of just emoji, and I think I have. Let me double check if I ever output the files for that. Is this the right kernel? We're gonna find out. So a while ago, I was doing work. I don't think that's gonna be actually. A while ago, we were doing a series where we were doing emoji analysis, and part of the thing that we had as the output from that was that we had a stock market prediction, messing with Julia, Twitter stock market, a data set that we put together that has information on character encoding, Python namespaces, job postings, salaries, Kaggle kernels, emoji analysis. Here we go. So we ended up with a list of emojis that are used together, and it looks like I don't have an output. Do I have an output? Okay, I just have this one visualization. So what I'm gonna do is I'm going to edit this, and I'm gonna get out just, I'm gonna save out just that list that we had, so we can use that for our model. Because it doesn't make sense to, it really doesn't make sense to use deep learning unless you have a lot of examples. I don't know, I probably wouldn't start turning to deep learning instead of, I don't know, some sort of regression until you had over 1 million data points. At that point, I'm like, yeah, okay, that makes sense. I don't know, have you guys seen there's an Oh Really, let's see if I can find it. Oh Really, networks for small data sets, I think it's, no, I still don't want O'Reilly. I want, well, none of these are helpful. I wanted the parody O'Reilly books, and I can't find them, so I'm just not gonna mess with it. Okay, and once we have all of these, let's save them out. I don't care about the entropy at this point. Text entropy validation. I'm trying to figure out at what point I have the particular, I think at some point I add all of these together. Yeah. Save.csv, I think is what. Oh no, it's ggsave. Ggsave. I'm pretty sure it's ggsave, and I'm pretty sure that's tidyverse. Let's double check. You still fitting? You still fitting? Scroll. It was after the entropy. Here we go. I'm pretty sure it's ggsave is the thing I want. And then I'm just gonna save Twitter emoji. Actually, first I'm gonna double check with Iris that this will work correctly. Can I just say no? Is that gonna work? So this is the input data we're going to use if I ever figure out how to use this function. Oh, it's only for ggplots. That's right, because the function is write.csv. Oh my god. This is what happens when you eat too many donuts in the live code, y'all. Kernel asks, was it this Oh Really? Yes, that's exactly what I was thinking about. Yes, that was the exact one. It's adding Hadoop to my resume, the pocket guide, effective Hadoop on small data sets. Yes. I don't want to call it Iris, I want to call it Twitter emoji. And this particular one is in save. Of course it wouldn't be. So I'm going to commit and run this, and then I can add this notebook as a data input to this notebook. See, tricksy. And then the file that is output when I commit this data notebook, because I'm saving it out, I can use as a data input to this. Yeah, see, pipeline all works together. And it's still training. So that is what I'm going to do for my data. And these are a bunch of emoji from various Twitter accounts, and I have extracted all the emoji that are used together. So if somebody used multiple emoji in a tweet, I have sorry, if somebody who uses multiple emoji and they're next to each other. So this example, which is I have no idea what that is. Box with buttons emoji next to the camcorder emoji, then I would have both of those as a set. And so my goal, I think, is going to be, given an emoji, predict what the next emoji in the sequence will be. So we can do sort of like generating an emoji sequence. Rachel, doesn't it make sense to do this with a hidden Markov model? You absolutely don't need to build an LSTM to generate this. Correct. Yes, you are 100% correct, but I'm doing it anyway. And it's training. Hello! So right now we're watching our model train, and by ours I mean Dan's. And this should identify sign language hand shapes, and then we're going to adapt this code to generate emoji. So the first thing I want to try, and I'm going to be honest, I have never used Python Keras before. I've only used R Keras and Python TensorFlow. I don't know. I've had like weird gaps. So I'm going to have to look up some stuff in the Python documentation. And particularly the thing that I am interested in is, I think it's just LSTM is the name of the layer, but I want to double check that. You done running? No, it's still running. And I can check that in versions. And this one's going to take a while to run. It's pretty crunchy. What am I looking for? Oh, wait. Keras LSTM layer. Recurrent layers. That is what I want. All right. Base class for recurrent layers. So LSTMs are a type of recurrent neural network. I don't need anything convolutional. I think I should be fine there. Simple RNN. Here we go. Cell class for LSTM layer. And right now, I mean, NACL is happening. The North American Association for Computational Linguistics is meeting even right now as we speak in New Orleans, and I'm not there, and it's fine, but all my friends are there. But so as of like the last major NLP conference, thank you. Sri just sent me the link. As of I think it's just the same place. Oh no, it's slightly different. Oh, I see. This is a cell and that's a layer. Gotcha. As of the last major NLP conference, bidirectional LSTM with attention had state of the art in most of the major tasks or some variant thereof. So currently that's what I recommend, but we'll see what people are saying after NACL. Who knows? It's a fast-moving field, and I haven't been on archive this morning, so could be anything. It's the... Oof. I would not recommend TAN activation. There we go. Okay. Recurrent activation, use bias, kernel regularizer. We're not going to have to mess with a lot of these things. Return sequences false. Oh, so this is how I think you would have to have a forward and then a backwards, and that would be bidirectional. Sorry, I'm just reading at this point. Okay, yeah, so I think this is the thing that we want, so excellent, and this is done. So if we look at the notebook, we can see it's all compiled and pretty, and then if we look at the output, we should see, we should see our file with all of the information that we had, and these letters are flag emojis. That's just how they render. Excellent. So this is going to be our input, and we're going to figure out how to generate the next emoji in a sequence given this input. My strong suspicion is that the next emoji in a sequence will always be the exact same as the current emoji in the sequence. But you know what? I could be wrong. We'll find out. There's this one again. What is this? What is this emoji? Desktop computer emoji. Oh. My home computer is Windows, which would explain a lot here. That doesn't... Okay. I guess. It's supposed to look just like a monitor. It does not. Okay, so that is our input data that we're going to use. Is it done training? Excellent. And it's done training. Okay. So at this point, now that we have a trained model, we are going to destroy it. No, we're just going to start modifying this so that we can do the same thing, kind of, except we're not doing labels. We're generating the next in a sequence given text. So we don't want con2d, we want LSTM. We still want to do sequential. There's another option where you can be more specific in what you're doing. Sequential is sort of like the less hands-on version of getting stuff done. We still want to set the seeds. We definitely don't need any of this. Like, this can all goodbye, nuking all that. I'm trying to decide if we are going to use any of these libraries. I don't. Are we going to be... We don't have to loop through, so you'd use glob for like looping through files and interacting with your file system. And we don't need to do that because this is all in a, the data from our output over here is all in a nice, what's this called? Oh my God, data frame. Wow. It's in a data frame already. So we're not gonna have to interact with the file system a bunch. We can get rid of that. I hate Matplotlib. I hate it. Are we gonna need anything with NumPy? I don't know. We're definitely going to want, I don't know what CV2, so I'm going to get rid of that. We're definitely going to want to import pandas as PD so that we can read in our data frame. Do we want random? I think we don't. I think that was used just to like pick random sequences from the list of files. Some random files from the list of files. So I think at this point we can pd.read_csv. Oh, you know what's not going to work is this until I add the files that I actually want to use. So I'm going to add a data set, and this is called emoji analysis. Hope it's thinking. Ah, there we go. Oh, and I actually want to be in kernels. No, it's there. I promise there's a thing called this. It's thinking. Oh, maybe it cares about case. What if I just copy and paste? I think that might be easiest. Another potential wrinkle is that this is I believe this is private. Sharing it. Yeah, okay, so this is a private kernel, so it may take it a while to find it. It's private to me, so I have access to it as I should. Come on. And I think what I'm gonna do actually, so I'm thinking about this. So I'm interested in guessing the next emoji given the current emoji, but some of my emoji sequences are actually pretty, what's the word I'm looking for? Short. So if we look at our data, I'm trying to figure out what the size of the input data should be. So on Twitter, I promised to futz around with tensors and dimensions for a while, and don't you worry, that's definitely gonna happen. Yeah, there we go. I'm gonna add this. Did I click bad? I'm not clicking good today. There we go. So we have this plot that was the output, and then we have this CSV file. We didn't have to download and upload and do all that shenanigans. Right, so if we look at error occurred while retrieving the preview. It's probably just not finished loading in. So if we look at these, so looking at a sequence, some of them are fairly long. So we have like these sequences. And I think for this, I'm going to use this that has the modifiers in it and not the one that doesn't have the modifiers, because I think it's interesting that there's variation in hand color here. But you'll notice that some of these are like 4, 4, 4, 3, 4. There seem to be quite a few things of length 4, quite a few of things of length 3, but there's a lot of 2s and a lot of 1s, a lot of things that only have one emoji. So I am thinking, should I look at a sequence of length 2? So that's going to be an input of 1 and an output of 1. And it may not capture. So if my training sequence is 2 characters, I can't give it the second character because that's what it's predicting. I can just give it the first character. And that's, well, I mean, so there's a fair number of emojis. There's around, 11 just came out. Unicode 11 just came out today. Emojis are not supported anywhere yet, the new emojis, but keep your eyes peeled. That's not enough. It matters a little bit. It certainly matters for like the shape of the tensors that we put in. So I could do a longer sequence as well. Like, does this emoji have a big impact on this emoji, and do I want that to be captured? I think 2 and 1 should work. Let's try that to begin with and see how that works. All right, so let's read in our file first off. Oh, yeah, because I didn't actually tell it a file to read. And you can see the file from the kernel that we added. We should call this emoji. Oop. Accidentally using all of my shortcuts. Emoji data. No, that's not going to work. Okay. Yeah, I'm just thinking. Let's try 2. So 1 input, 1 output. And again, deep learning is just overkill for this. It's really bad overkill. Because we're I also don't know what TensorFlow's Unicode support is like, so we might have to one-hot encode these. We might not, though. It depends on how they handle modifiers, because like an emoji plus a skin tone modifier is technically 2 characters. So depending on how that gets handled under the hood, that may give us trouble as well. All right. What is the column we want called? Emoji. Oh, that's easy to remember. Was that a thing? Okay, and let's actually sample 10. No, I can't do that. There we go. So what we're gonna want to do is get all the sequences of length 2 or more. And then for sequences that are of a length greater than 2, we want to split them up. So this will be a valid input, and this will be the thing we're using to predict, and this is going to be the thing we're predicting. And then this plus this. So this would be one input, and this would be another input. Actually, I can... Here's LSTM. Inputs of different lengths. Maybe we don't have to normalize for this. Ah, that's exactly what I wanted to know. Blah, 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 blah. Predicting the next item element in a sequence. Oh, that sounds familiar. Oh no, cookies. Have you guys been enjoying your GDPR emails, hopefully? I've been getting a lot of updated terms of service. Blah, 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 blah. Blah, 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 blah. It doesn't want to pad the data. So that's one thing we could do is we could just add like 0 after all of these sequences so that we'd have like one emoji, 0, 0 to however long we want our longest sequence to be. Can I correctly build a variable length input in Keras? Oh, okay. It doesn't matter. So we can just look at all of the ones that have length of more than 1. Okay. Model, blah, 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 blah. All right. Unknown time span, fixed feature size. Okay. So this would be like, you don't know how many letters you have, but you know that there's only 200 possible letters. Yeah. And I don't know how many unique emoji there are in this data set, which is probably something we should figure out, huh? If I were Python, I would have something like n unique chars. Number of unique characters. In pandas column. Close enough. Count unique values. Unique. I don't care about the values though. I want the unique characters. Values from a list. Still not the thing I'm looking for. Maybe I should get rid of unique. That might be what's throwing it off. Ah, unique, you say? I'm gonna keep this in just so I can have myself a little peek at the data. Okay, but this is not... So this is the number of unique elements, but I'm interested in the number of unique characters. So I think what I need to do is I need to split this into... split each item into each of its unique characters. Use the length column. So that's, oh, no, I can't see it. All right, well, we'll do it the old-fashioned way. Add all rows and then see unique characters in a string. Yeah, that might work. I'm gonna really quickly look at the emoji. Head. All right. So the problem with using length is that we don't necessarily know that this character is the same as this character from looking at here, and I'm interested in the total numbers of. Oh yeah, but there can be repetition. So Giovanna says unique characters equals data square bracket data square bracket length equals 1 square bracket. And the problem with that is there might be unique characters that exist in things like this. So maybe the angry face never shows up by itself. And that wouldn't necessarily... And it would get all of the ones of length 1, but it wouldn't... Wait. I'm gonna work through this again. So we're looking for the things... So we're looking at data where length is 1. Yeah, so we might not see characters that are in multi-character spans. And if there's characters that only ever show up with other characters, we won't necessarily get them that way. So yes, good instincts. I don't think it's going to work in this case because there's repetition within here. Paste entire pandas column into single string. So I'm going to try Susano's example. A str.cat. So I think I'm going to turn it into a single thing, and then so that should be a series because the columns. And is this a... Oh. Huh? Oh, this is going to be very big. I shouldn't have printed this out. Okay, excellent. And now I can get all the unique characters from here. Man, this looks like a horrible wallpaper. This looks like something somebody would put up in the subway. I think this is going to look at elements and not characters, but well, let's try it out. Yeah, okay. Oh, emoji. We've gone down a horrible rabbit hole. It would be a cool wrapping paper. Count unique characters in a string Python. For loops. This seems fairly inefficient. I don't know. Maybe it's not. I'm hoping that there's a function for this. Oh my god, these are even longer. I just want... These are all like exercises for people learning Python. I don't want that. I want the function that will do it for me. Well, I guess I'm doing this. Maybe the set data structure, that should add only uniques. I think that would work, except at this point we have a horrible string. I think sets only works with each of the unique elements in a tuple. So this has one element if you're looking at it. D-type? D-type? Maybe D-type is not defined. I thought that's what it was, but maybe it's not. List of all unique characters in a string. Yes, it is the set data structure. Thank you. You guys are helping me out. All right. And try this. Nice. And then all we need is the length. This took way longer than it should have. A Rachael story. Oh, right. I always forget len is in the global namespace. Okay. We have 790 unique emoji, which is not that many, all things considered. Like I said, I think there's like 2,000 unique emoji, and more now because it's Unicode 11 just came into effect, which is emoji 7.0. Does that sound right? How many unique emoji do we have? Question mark. Okay, I think we can get rid of this cell now. So, oh no, did I leave the answer that I actually was using? I did. Oh no. There we go. And the example was... Oh, we were already on it. So it was the input. So the shape of the input should be none. And in our case, it should be 790 because that's how many emoji we have, and not 200 because that's how many whatevers they had. I'm going to actually copy and paste this so that I have it later. Nope, not that direction, the other direction. So that I have it later when I want it, because it's about time to start wrapping up. Believe it or not, this one has gone by fast. Mainly because it was mostly just sitting watching a model train, I think. I think we do need to get rid of all the emoji that only ever occur by themselves, though, because there's no sequence there. Well, that tells us nothing about co-occurrence if it just occurs by itself, right? So I think we can just schloop and get rid of all of those. Capital N, none, because that's what Python's like. Like so. And then the 20 here is for the where's the 20 coming from? Data 1. Okay, so I know where the 200 is coming from. And the 1 is just because we have one dimension. So this would have been 3 when we were working with images, because it would have been... Intel MT says number of layers? Units, okay. So this has 20 units. And then we have... Oh, they're not using the sequential model. Okay. So we're not going to be able to use this exact code, but we'll probably be able to I don't like to say cannibalize, but, you know, use a good portion of it. Yeah. Okay, so that will be our... So next week, we didn't even get to munching around with tensors. We started thinking about dimensionality. So next week, I won't be here. There won't be anything next week because I'm visiting my family. I'm going to eat so many peaches. It's going to be amazing. So the week after next, we will get started preparing our data, which is all read in and everything. We just have to sit down. Features. Emoji. So we're just going to have to sit down and figure out how to get the data that we have into the shape that we want it to be, and then we will begin our prediction process. And I'll probably spend some time reading up a little bit more on the Python version of Keras, which is much more fully featured. All right, so I will see you guys in 2 weeks. Thank you for joining me and have a really good weekend. Bye.